Hi everybody. Well, today let's discuss the branch instructions. Okay, the branch instructions are very important. Okay, especially when we run a long program. Okay, we need to make a decision to see we go this way or we go that way, or we branch or not. Okay, so the branch instructions are very important. In general, we branch or not. Okay, the based on the testing result of our operation. So the testing result of our previous operation in general are saved in the condition code register (CCR), as we talked about before. So we have 80 bits of condition code registers in general that contains the previous operation result. So we branch out the based on by checking one or more bits of the condition code register flag bits. So we got to become familiar, or we got to revisit the condition code register flag bits before we go to branch instructions. So again, I want to remind you guys about where we are now. So we are still discussing the 7 categories of 68 HC12 instructions. So we finished the data transfer. We finished about 2 weeks ago, and then we discussed the arithmetic operation, mainly about addition, subtraction, multiplication, and divisions. Then last week we discussed the logical operation and the bit manipulation. Yes, we finished this even in previous lecture. Okay, logical operations mainly for logic and, or, and exclusive or, and complement. When we go to the bit manipulation, okay, it's mainly about what? Mainly about cleared bits or set bits. Okay, they mainly design what? To play with individual bits of a value in memory or in the register. So make sure those manipulations are different from data manipulation. Those manipulations in first category, they're about the data manipulation. They're mainly about what? About rotation and shift. Okay, rotation and shift. When we say shift means what? We have arithmetic shift, logic shift. They are to manipulate a whole value. So when we come to the third category, those manipulation is to manipulate a particular bit, one bit or few bits like this. Then we also talk about a data test. Okay, data test. Yes, we test the value to see if that value is what? Is positive or is negative or not. Yesterday we discussed this. And we talk about what? We have the BITA and the TST. Remember, I show you example about this. We all test the value to see if this value is positive or negative. BITA, BITB, or this we discussed. We talked about this yesterday. Today, so we are come to here. We come to the fifth category out of 7 total the categories of 68 HC12 instructions. It's very important. So be aware where we are now. So as I said, before we get to the detailed branch instructions, now we got to be familiar with the condition code register flag bits. Why? So I already mentioned why we need to be familiar with condition code register flag bits, because in general the branch instruction is run or not, or we branch or not. It's based on the testing result of previous operation, or it's based on the previous operation result. So the previous operation result, okay, are saved, or some information about the previous testing result are saved in the CCR, in the condition code register. Okay, so where does value come from? They come from ALU. Remember, I show you ALU. Yes, come from ALU. Remember, okay, in lecture 1 and lecture 2, we discussed we have 4 modules of computer systems. Hopefully, you guys still remember those. They are the CPU, they are the memory, they are the bus, and the I/O devices. And I also mentioned within the CPU, we have 3 modules. We have 3 main components. They are control unit. That's the brain of a computer. So that's the brain of a CPU, which is the brain of a computer. And so we have control unit CU. We have ALU, arithmetic logic unit, and also we have some internal registers. So those 3 are main components of a CPU. So ALU is one of very important components within a CPU. So the job we already mentioned is the you see from its name, arithmetic logic unit. So it's mainly designed to perform what? The arithmetic operation and logic operation. So we can simply consider it like a box. It's what mainly designed to do some computations, and both arithmetically and logically. Now, when we go to the microcomputers 2, that course and in spring, then we need to learn to design control unit. So we need to learn design an ALU. So right here in microcomputers 1, we learn how to use it. So we program the computer. So we need to write a branch instructions based on the values of condition code register. In general, these values are provided by ALU. So the ALU, it provides inputs to the 8 bits. So the value of condition code register 8 bits, we call it flag bits, come from ALU. ALU. So in general, as we talked about this long time ago, and when we discussed the other instructions, I show you every time when we discuss that category of instruction, we go to the table. I show you the table at the end of the book, and the last 8 columns, they show this the value of condition code register when we run that instruction, right? So basically, as we remember, those bits of CCR that tell us what's going on with previous operation. So tell us some information or the characteristics. Right, here's information or the characteristics of the result of the previous operation. So when we say the result of the previous operation is mainly about arithmetic operation and logic operation. That's why, because here we come here, managing to perform it by ALU. However, some bits in the CCR indicates the testing result of previous operation, while some other few bits, they mainly control the microprocessor hardware. They controls the hardware operation of microprocessor. And then while some other bits, they really indicates the test result of previous operation. In other words, not all the bits of condition code register that indicate the test result of the operation. So let's take a look at all these 8 bits. So hopefully you guys still remember those bits. They are here. Those are the bits right here. Those are the bits here. So we give them different names. We call the flag bits. So if you start from here, this is CCR 8 bits. So this is we can simply call this to be the bit 0, bit 1, and bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7. So from bits 0 to 7, totally 8 bits. So as I mentioned, those 8 bits, they're used to keep track of the program execution status. So the programmer, user, can know what's going on with my program or what's going on with the operation of our program by checking these bits, something wrong or everything's fine or not. It also controls the execution of conditional instructions, and sometimes they can enable. So we can enable or we can disable the interrupt handling by configuring some bits. Okay, of course, by configuring the hardware bits, because I mentioned here some bits indicate the test result, while some other bits controls microprocessor hardware. Now, because all these bits are in binary, so the value is either 1 or 0. So, or we said with this bits can be set or can be reset, or can be clear. Sometimes when we say reset it means it's clear. Or at the beginning you set some values. You configure this flag bits, but however, these bits or some bits may change during operation. Yeah. Also make sure. So let me cleanse out, and then we can talk a little bit more about it, because this is very important. So we also give a name to each bit. Okay, based on the role of this bit, or based on the functionality of each bit. So let's start from the low odd bit. Low odd bit here. It's called the bit C, or C flag bit, or flag C, or we can simply call it and the C bit, or more commonly we can call the bit 0. Anyway, why it's called C? Because it's carry bit. So this bit 0 is carry bit, indicating information about if previous operation has carry or not, involved carry or borrow or not. So we can call it borrow or carry, because we can simply consider borrow as a special type of carry. This is bit 0. Bit 1 here is overflow bit, so we simply use V. V right here is overflow. Now we can simply say this bit is to tell us if previous operation hasn't run or not, has data overflow or not. We'll talk a little bit more about this. Then bit 2 is the 0 bit. Okay, 0 bit. That means if previous operation result is 0, then this bit is 1. If not, this bit is 0. The bit 3 here. Okay, make sure this is half. Let me put a mark right here. This is half. This 4 bits here. Yeah, this low order 4 bits. This is high order 4 bits. It's half byte. The bit N here is negative bit. That means to tell us, okay, if previous operation produces a result of 0 or not, a negative value or not. If the previous result, if previous operation produces a negative value, then this bit, the bit N, is 1. If not, it's positive, okay, then this bit is 0. The bit 4 right here, the bit 4 here we go, is I. Why is I? Because it's interrupt mask. We talk a little bit more about this. This I can have something to do or similarity with X. X is external. X means external. External interrupt mask. We talk these two together after a while. One is interrupt mask. One is external interrupt mask. We talk a little bit more. Then the one between I and X is H. H is called the half carry. So the half carry means when you do previous operation, if previous operation involved a carry from bit 0 to bit 1 or not, or involved a borrow from bit 0 to bit 1 or not, this half carry. In other words, if previous operation involved a borrow or carry from low order byte to high order byte or not? If yes, then here H is 1. If not, this is 0. The leftmost bit is called stop disable. And when we move forward, we'll see for the 68H12, okay, we have one instruction called stop. Okay, stop. This is called what? Stop instruction. We can disable it. So okay, if we disable this instruction, this instruction will not run. Instead of what? It will work like a what? No operation. When it works out this way, it will save energy. It will save energy. Yeah, we talk a little bit more about this. So anyway, I want you keep in mind, okay, that we have this 8 bits. It's very important. And these 8 bits in general, okay, are the conditions, okay, for tester. Therefore, the conditions that what in general the CPU check, so that what CPU decide if you branch or not the best our program. It's very important. So here I put all the 8 bits of CCR together to show you where the bits indicate the result of arithmetic or logical operation. Where are the bits, okay, the so-called what to configure hardware. Okay, here I mentioned some bits, okay, they control hardware processor. Okay, the money controls hardware. The money controls what? Hardware. The hardware operation. So here we go. The bits we are more interested, or the bits mainly served as a condition of branch, are those bits. We particularly, I should say here, arithmetic and logical operation. So the bit C, bit V, bit Z, bit N, and bit H, or the bit 0, 1, 2, 3, 5. Those are the testing bits. They mainly indicate a test result of arithmetic and logical operation. Very, very important. So C is carry bit, V is overflow bit, Z is 0 bit, N is negative bit, and H is half carry bit. So we are very interested in these bits. While some other bits, here I show you those bits. Bits I, this is called interrupt mask. X, external interrupt mask. And S, those are mainly for hardware control. In general, when we study branch instructions, okay, in general, we never check those hardware control bits. So we can simply ignore the value of these 3 bits when we involve branch instructions. So in other words, what those 3 bits in general do not affect our decision about a branch. So the bits we need to check, or they really affect a branch or how we branch, is what? Is these 5 bits. This is C carry bits, V overflow, and 0 bit, and M and is negative bit, and half carry. So we will focus on the arithmetic and logical operation bits. Now, before we go to our discussion on the 5 bits, on the 5 arithmetic and logical operation bits, so let me simply introduce the interrupt. Why we introduce interrupt? Because, as I mentioned here, the bits X and I, they are interrupt mask. Those bits. X and I, very important. So make sure I is interrupt mask. X is external interrupt mask. Okay, so 1 is bottled water. So X shortest water is a mask. Okay, is mask bit mainly for the external interrupt. Okay, while I mainly shows a general interrupt mask. So we talk about what a mask is first before we get to discuss the X and I. Interrupt, you do something and you feel interrupted. Or like here we go, we are making a video of my lectures, and I don't want somebody to interrupt me. I put a sign on my door said do not disturb, don't interrupt. So interrupt here for the microcontroller is similar to the scenario I just introduced. It is considered there is a special event that requires the CPU, something to do with CPU. Special event that requires the CPU to stop normal program execution, to stop what you're doing right now, normally, and perform some services and do something else, perform some services related to the event. In other words, you do something now, normally, but something happened that need to be taken care of right away by CPU. Something like what? Feel like something is more important, or you have to stop what you're doing right now and take care of that. Here are some examples. Input output the completion operation is considered to be interrupt to CPU. Timer timeout considered to be type event for CPU. Interrupt event for CPU. Illegal opcodes. This is kind of dangerous. All these kind of they're serious. Illegal opcodes. Sometimes the CPU run program and found out you have illegal opcodes, and you never define this. You never define this opcode in your 209 the instructions. Something wrong. You got to take care of this. That's kind of interrupt. Your normal operation is interrupted by this so-called unknown illegal opcodes. It may cause a special It may cause a very danger to your software systems or to memory. So you got to take care of them very quickly. Or the arithmetic overflow. Okay, this mainly is results shown by V. And also in general, if the flag bits V is 1, that tells you that the microcontroller involved arithmetic overflow operation. So we'll talk a little bit more about this in a while. Then divided by 0. Sometimes your computer running, your CPU running, but it involves an instruction which divided by 0. That's not allowed. But we should not divide anything by 0. So it's also considered to be type of interrupts. Now, interrupts are planned but unscheduled high priority event. It's a type of event, and CPU knows what to do. CPU knows how to take care of that. So it's planned. But you don't know when it will happen. So it's unscheduled. If you know scheduled, then it's easy. Also make sure it's high priority. Because you mentioned there's something like is more important than what you're doing now. Okay, yeah, it's planned but unscheduled high priority event. Also, the interrupts are divided into the maskable and non-maskable. So we have maskable interrupt event and non-maskable interrupt events. So what's the difference? Which one is more serious? Which one is what? Which one is not serious? It's not serious, so it can be ignored. Here we go. The maskable interrupts This one is not as serious as non-maskable. Maskable because like what? Like you cover your face, you put a mask on your face, you pretend you don't know that. So it's maskable. So it can be ignored by CPU. Or CPU decide what you ignore or not. Or another CPU can ignore it. So this type of interrupts are called maskable. So a maskable interrupt must be enabled before it can interrupt the CPU. In other words, what you have to make the bits control this maskable interrupts to be 0, so it can interrupt the CPU. So you must clear it. Okay, this interrupt so it can interrupt CPU. If you make it 0, it's not going to interrupt CPU. So here we try to say you make it what the control bits to be 0 to enable it. This is a little bit like what idea and philosophy is different from what we thought before. In general, we thought what you make it 1 to enable it, but here it's not. Here you make it 0. You make it what is control bits to be 0 to enable it. Now, if I interrupt, if it's very important, okay, if it cannot be ignored by CPU, so this is very important. CPU cannot pretend they don't see it. So you have to take care of that. You cannot be ignored. Then this type of interrupt are called non-maskable. Okay, you cannot cover your face and say that I don't see it. So I don't want to pay attention to that. No, that's not allowed. Because this type of interrupts are very important, non-maskable. So this type of interrupt even cannot be turned off by user. It's because it's very important. So anyway, keep in mind we have 2 different types of interrupts: maskable and non-maskable. Maskable and non-maskable. Non-maskable are very important. They cannot be ignored by CPU. Even it cannot be turned off by a programmer. Maskable, well, it's easy. Maskable, well, okay, we leave CPU to take care of or not. But if you want maskable interrupts to be able to interrupt CPU, you have to make it what? Make it its corresponding control bits to be 0. In this slide, I show you that we have 3 different types. We have 3 different types of non-maskable interrupts. So for the 68H12 microcontroller, we have non-maskable interrupt and maskable interrupt. Maskable interrupt here are many more, because what they are designed so CPU can choose to ignore them or not, or can serve them or not. Non-maskable, CPU have to take care of them. CPU have to serve this request. So we have 9 different types of the maskable interrupts, and 3 different types of non-maskable interrupts. So we will discuss all these details when we move forward, when we go to the hardware, when we go to chapter of hardware in chapter 6. But here, let's take a look at some of these maskable and non-maskable interrupts. Non-maskable, unimplemented instruction trap. That's very important. So like what we have illegal opcodes, or it's dangerous. Okay, if CPU fall into that circle, okay, or that range, CPU may never out. So like trap, is what right here said what is never designed for the CPU to run. It's very important. Or software interrupt instruction SWI, and external interrupt routine. External interrupt routine. All this that belong to non-maskable. Sounds like what they kind of very dangerous. Like what you may fall into loop. So like what like you may have a bug like this. So it may make a CPU to stay there forever, repeating doing this forever and never out. This is non-maskable. This is very dangerous. In comparison, here I show you some of the maskable interrupts. The IRQ, internal the interrupt routine. Internal interrupt routine request from internal, and real-time interrupt, timer channel, timer overflow, path accumulator overflow. Like sometimes we have value in the accumulator but it's full. Okay, this accumulator assume now only contains 8 bits, but now you have to store 9 bits, or path accumulator. Okay, yes. Sometimes what you have accumulator, you count how many times this event happened. Okay, but now assume now the number of events happened with more than what the maximum value that is what the path accumulator can contain. Then this is belong to maskable interrupt. And some more about the communication interface, serial peripheral interface, and serial communication interface, analog to digital conversion, and keep wake up. Those mainly about hardwares. Those are something about the interrupt, about hardware. So we will discuss when we move forward to hardware part. Now, for the maskable interrupts or non-maskable, okay, well sometimes what a programmer is allowed to configure them or to control them. So non-maskable interrupts is controlled by X bit, by this bits, this one. Okay, non-maskable. And the maskable interrupts are controlled by I bit, by the bit I. One is by X, this is by X, this is by I of CCR. Okay, for the non-maskable interrupts, in general, when you reset your machine, when you reset your systems, that turns the interrupt system off. Okay, when you make it 1, it will make it 1. But when system get into normal sequence, then X becomes 0 by itself. So in general, the non-maskable interrupt is turned off when you make X bits to be 1, and is turned on when X bits is turned to 0. So you make 0, you re-enabled. Assume at the beginning when you restart the machine, this X bits is 1. That's turn off the non-maskable interrupts. Then, shortly, when system becomes stable, X turns to 0 by itself. Then when it turns 0, that re-enable the interrupt systems. When the interrupt systems is re-enabled, so it can interrupt our CPU. So make sure when it's 0, we enable the non-maskable interrupt. When it's 1, we turn off. Well, similarly for the maskable interrupt. Okay, so at the beginning is turned off. Okay, by making the bit I to 1. Or in other words, if you make the I bit to 1, so this can be done by programmer, by a user. If you make at the beginning, you change the I bit of a condition code register to be 1. That turn off this maskable interrupts. Then it remains in off until you enabled. Until your program enabled. So you enabled by making the bit I to be 0, similar to the non-maskable interrupts. So 1 disabled, or 1 turned it off, 0 enabled. When you make 0, you enabled, that means what? They can interrupt the CPU. For the maskable interrupts, when they interrupt CPU, CPU can ignore it or not. So CPU decide what you take care of this interrupt or not. For the non-maskable interrupt, when they interrupt CPU, CPU has to serve them. That's it. But the bit I and X in general has nothing to do with branch instructions. They only tell us about about hardware control, as I mentioned here. Okay, they only control microprocessor hardware. While we are more interested, when we study branch instructions, we are more interested in to this 5 bits, to this X, to this H, N, Z, B, and C. We are very interested in these bits. So let's discuss these 5 bits we are more interested for branch. Let's start from carry bit 0, this bit. I assume you guys know very well about carry bits. The carry bit, it indicates the result of testing for carry from most screen bit or left bit. Or it indicates if my operation or if the CPU operation or the arithmetic operation or the logic operation involved a carry or not. So in other words, okay, if this bit is 1, that means the previous operation it has carry happened. It has carry operation happened. So in general, okay, when we do addition, then we may have carry. When we do subtraction, we may have borrow. Yes. Okay. No matter it's carry or borrow, if it happened, if carry happened or if borrow happened, then all make C to be 1. So it will set the carry bit. Okay. So keep in mind that both the addition and the subtraction can make carry bits to 1. So when you do addition, if your addition operation result in a carry, that makes C to 1. When you do subtraction, if your subtraction involved a subtraction, then it also make. If your subtraction involved a borrow, it will also make the carry bits to 1. In addition to carry may caused by addition and borrow caused by subtraction. Data manipulations. like shift and rotation instructions we learned in first category may also cause the carry bits to be 1. So remember shift and rotation instructions we learned in first category, and I even mentioned at the beginning of today's lecture. If the shift out or one into rotation, if the rotate out 1 bit, if it's 1, in general this bit swap it also goes to carry bit. That make it carry bit to 1. In other words, when we do rotation or shift, no matter it's arithmetic shift or it's logical shift, when the bit shift out, that bit, if it's 1, that bit is goes to save it in the carry bit. So we shift out, it goes to carry bit. So if that bit shift out is 1, then can make carry bit to 1. If the bit we shift out is 0, then the carry bit is 0. So it will not affect when the bit is 0, it will not affect the carry bit. So I like to and go back to lecture 5 to show you where we can see the shift and the rotation and rotator instructions. They can also make the carry bits to 1. So let me get to lecture 5 here, or the alternate here. Here I show you yes, they're here. It's here. With rotation, excuse me. It's here. We have what? Rotation, large shift, and the arithmetic shift. Here we go. This is about our rotation. Rotation, here we go. No matter is rotate left or right. This bits, the bit 7, when we do rotation, left rotation, no matter its value is memory or in the accumulator, this bits it goes to carry bits. So if this bit 7 is 1, when you do rotation, this bit what? It dropped into C. All the C, the back, original C, before we do shift, value in the flex C, come back to fill the bit 0. Same idea for rotating right. So this bit here, bit left, means bit what? Rightmost, which is called bit 0. It's bit 0. Okay, we do what? We do rotate right. So if this bit is 1, we shift out. So this bit drop to C. So make the carry bits to be 1. If this bit here is 0, then make carry bits to be 0. Then means what? Means carry bits 0. That means we don't have carry. Same thing for shift. This shows what? A logical shift. Right here we see this. Shift. So for shift here, assume now this bit 0. This bit 7 is 0. Then when we do logical left shift, then this bit shift out here. This bit goes to C. So C will make a 0. So if this bit is 1 here, if this carry bit sub 7 is 1, we shift out, make C to 1. Same idea for D or the logical shift right. So this bit goes here. This bit goes here. Even for the arithmetic shift, because arithmetic shift right here is pretty much the same as logical shift, except the arithmetic shift right. This one. But for right here, we got still the bit 0 goes to C. This is for left. So this bit, so after we perform this arithmetic shift, C will be 1 if the bits shift out is 1. If the bit 7 is 1, before we shift. So before we shift, if bit 7 is 1, then when you do shift, he shifted this bit out. When you shift out, this bit what? It goes to carry. So it will make the carry bit to 1. So that's what we just reviewed about the rotation and the shift can also cause the carry bits to be 1. Excuse me. Okay, so carry, borrow, shift. Well, next bit right here I show you is bit V. Bit V is interesting. Bit V, it indicates the result of testing for tooth complement overflow error. So like what? When we do some arithmetic operation, in general they happen between two numbers. These numbers, they must be the tooth complement numbers. In other words, these numbers in general are considered to be a sound number. When we do some type of arithmetic operation, especially when we do like addition or subtraction, okay, it turns out what our result, okay, from the point sign, okay, is wrong. That's called the overflow error. If that happened, that's going to make this overflow bits to be 1. Very simple example. Like what? You are adding two numbers. Make sure these numbers must be the tooth complement numbers. They're the tooth complement numbers. They're sound numbers. When you have a number, if you hope to check to see if they cause overflow or not, overflow error or not, these numbers must be considered to be a sound number. So if sound number, assume now we have two numbers. The sound number, we assume now they consider to be positive. So their positive one, the leftmost bit is 0. And their negative one, the leftmost bit is 1. Assume now you have two numbers. These two numbers, what? For both numbers, the leftmost bit is 0. Now when you add these two numbers, so they're both positive because they both have what? Leftmost bit to be 0. If you add these two positive numbers, it turns out the result is a negative number based on the arithmetic addition. That's unreasonable. You added two positive numbers, but our result is negative number. There's something wrong. Arithmetically, overflow happened. Overflow error. That's going to make the V to be 1. Okay, or sometimes what? You added what? Two negative numbers. It gives you a positive number. You added two negative numbers, the result should be a negative number. But if the result is a positive, they also cause overflow error. Well, some other people, they consider what? The flag bits to 1 when they carry from the most significant bit and the second most significant bit are different. They're not same as a result of an arithmetic operation. So let me give you the 4 cases that may cause overflow bits to be 1. So I prefer start from addition and subtraction. In general, for addition is this. Let's start from addition. 2 cases. One case, is when you add two positive numbers. Let's use P represent a positive number. When you add a positive number with another positive number, if your result is negative, that causes overflow to 1. When you add a negative number with another negative number, n here means what? A negative number. Let's call it P1 and P2. P1 means one positive number. You add with another positive number. If you got a negative number, if your result is negative, then this will cause overflow to 1. Or when you add in two negative numbers, when you add in a first negative number and with another negative number, if your result is positive, that's something wrong. You add in two negative numbers, but a result is positive. There's something wrong. It's overflow. That may also make overflow V flag to 1. This is about addition. Subtraction may also cause overflow bits to 1. Subtraction is very reasonable. Assume now you subtract a positive number from a negative number. Okay, the result should be negative, but it turns out if the result is positive, then it may also cause overflow bits to be 1. In other words, we subtract a positive number from negative number. The result should be negative, for sure. But if the result is positive, that also causes overflow bits to 1. Similarly, okay, if you subtract a negative number from a positive number, you subtract a negative number from a positive number, okay, the result should be positive. But if our result is negative, that may also cause overflow bits to 1. So 4 different cases. In addition, we have this case and this case. For subtraction, we have this case and this case. All these four cases will cause V to 1. Will cause V to 1. So let me clean this out so we can see better. Yes. So let me show the cases here. This case, this case, this case, this case, all can cause V to 1. Any of them can cause V to 1. All other cases, V is 0. So make sure here, when I say P or P1, that means what? A positive number. So here, let me change right here to something called P2 here. Let me erase this first. This means what? A different positive number. 2. All these 4 cases, the 2 cases happened for addition, and 2 cases happened for the subtraction. Will cause overflow bits to 1. Something wrong. Overflow error, see? Overflow error. This is very important. Next bit here is flag bit Z. This one I think is pretty easy. I think that this one is very easy. That means what? If previous operation it produces a result of 0, that's going to make this flag bit 1. Otherwise, it's 0. Or in other words, what? When you do some operation, if the result of your operation is 0, like what? When you do subtraction between 2 numbers, if these 2 numbers are absolutely the same, when you do subtraction, our result should be 0. Right? Yes. If the result is 0, that means what? Okay, we need to make a z to be 1 to tell people, okay, our result involved what? I mean, it will tell people our operation involve the operation resulting value of 0. So z is 1. So if the value is 0, z is 1. If the value is not 0, z is 0. If the result is 0, z is 1. If the result is non-zero, okay, then the z is 0. 1 means what? It happened. 0 flag bit means what? When 0, when it's 1, means what? Yes, the 0 happened. When it's non-zero, when it's 0, okay, means what? When this flag bit is 0, that means what? Okay, the 0 operation not happened. So only when all bits of operation happen with 0, that's going to make z to 1, otherwise 0. Similar idea for negative number. N. If your operation happened, it produces a result which is negative. When you do some operation, no matter you do what, addition, subtraction, or multiplication, whatever, if the final result happened to be a negative number, in other words, what happened to be have the leftmost bit is 1, or is 1 byte, which means what? Most significant bit, okay, is 1. That means what? This number is negative number. If so, that's going to tell n about this. So we'll make n bit to be 1. So when n bit is 1, that tell people our operation it results in a number negative. Otherwise, it's 0. So when your operation produces a negative number, okay, then the n is 1. Otherwise, 0. So your result what produce number is negative only when its leftmost bit is 1. When leftmost bit of your number is 0, then your number is positive, as we just talked about right here. Then half carry. Half carry, as I mentioned, when your operation, no matter it's what, addition or subtraction, when your operation involved a carry from bit 3 to bit 4. Okay, as I showed you a moment ago. Like I will assume now, let me show you here. So now we have 8 bits operation. It's called a let me use different color. Bit 7, bit 6, bit 5, bit 4. There's four bits. Then we have bits 3, bits 2, bits 1, bits 0. Assume now you do operation. Okay. When you do assume now you add 2 numbers. Okay, this is one number. Let's call this number 1. Another number here we got, right? Yes, you also have 8 bits. Assume now you do addition or you do subtraction, whatever. When your operation involve the carry, or when you involve carry, like when we do operation, when we do addition, if you involve carry from bit 3 to bit 4. And that's why here we have another bit 3. When you add these 2 numbers, okay, and it produces a 1. Okay, so when it produces a carry to B4, here's some 0 or here 1. But you do involve carry from bit 3 to bit 4. That's going to make half carry bits to be 1. But if it happens between bits 1 to bits 2, in other words, when you do addition, if you have a carry from bits 1 to bits 2, but not from bits 3 to bits 4, then that's not half carry. Or you involve carry from bits 4 to bits 5, but not from bits 3 to bits 4, then half carry bits is still 0. Okay, so we involve, or same idea for what? For subtraction. Assume now we do subtraction now. it turns out that we involve a borrow, okay, from bit 4 for bit 3. We involve borrow from bit 4 here in order to perform the subtraction at bit 3. Then it's also called half carry. Because I said borrow is a type of carry, but for the subtraction. Like we consider the subtraction is a complementary operation for addition, as I mentioned way back in lecture 5, I think. So some people they simply say this type of carry is consider carry from is carry from, excuse me, I'm something wrong right here, from this byte to this byte, from this half byte to this half byte. Okay. In general, half carry bits is only used with binary coded decimal numbers. Okay, that's why we simply will carry bits from bit 3 to bit 4, from half byte from low order half byte to high order half byte, or from low order 4 bits. But it only happened from here to here. This counted, not from here to here or from here to here. Now, let's do some exercise. Now let me see. Well, probably it's good for me to leave this as some homework that you guys try at home. Then Then in next lecture I will show you this. So here, when we say we try to check what's the bits of this N or Z or V or C, is mainly about when we involve the arithmetic operation or addition or subtraction inside the instructions, inside the program. It not only show you the operation, but we do this type of operation in the program. Like we add some numbers into accumulator here, like this. Here we go. Then we involve addition. So we add a different value to the value we already loaded in A. Then we see what's our result. So this result will be shown. So the status will be shown by using these flag bits. So let me leave this like homeworks. You guys try at home. Then the next time, we will go over these problems, and we have some more problems. Okay, so that's pretty much we prepared for lecture. I think this lecture 11.